In this video, we will talk about how to train a classifier to provide flat or uniform dependency of signal efficiency on the particle parameters. Firstly, let's consider how to train a boosting over decision trees classifier to provide flat performance on the set of features. This example is based on the other boost classifier. This classifier uses the last function shown on the slide. In this function, gamma is a true label of an event, and S is score obtained for each event as the sum of predictions for all trees in the series. To provide the flat classifier efficiency or set of features, we modify the last function by adding a new term that is responsible for the flatness. Let's consider how this term works. Suppose that we would like to provide flat signal efficiency on a particle momentum. For that, we divide the momentum values into bins. Then, for each bin, we integrate the differences between the cumulative distribution of the classifier output in that bin and the global cumulative distribution of the classifier output. And finally, we calculate the weighted sum over all bins. Weight of a bin is a fraction of signal particles in this bin. This term tries to minimize differences between the global distribution of the classifier output and the output distribution in the bins during the classifier training. In case of the ideal flatness, this term is close to zero. The modified loss function provides a trade-off between classifier quality and classifier output flatness. The better flatness, the worse quality of particle type identification. And the balance is determined by the problem requirements you solve using such modification. This is just one possible modification of the loss function described in the original paper provided at the bottom of the slide. Consider results of these modifications. The figure on the slide is provided by the original paper. It demonstrates dependencies of signal efficiency from a selected feature, minimum distance from the corner in our case, for several classifiers for the same global efficiency of 50%. It illustrated as this global efficiency is illustrated as a gray line. Black curve in the figure corresponds to conventional other boost classifier without any modification of its loss function. This classifier has strong dependency of signal efficiency from the selected feature. The second curve with the name KNN other also represents a non-flat other boost classifier, but with other loss function. All other curves correspond to different flat modifications of other boost classifier. The results for the modification described in the previous slide are shown as the first red curve. It demonstrates much better flatness compared with conventional other boost. Consider how it works in the particle identification. This figure shows the dependencies of the pion efficiency from its transverse momentum at the LHCb experiment at CERN. The figure compared two classifiers for three different global efficiencies: 60%, 80% and 90%. The blue curves correspond to the uniform boosting, which is an other boost classifier modified as it was described previously. And the green curves correspond to the non-modified gradient boosting classifier on decision trees. The uniform boosting provides significantly better flatness of the signal efficiency for all three global efficiencies. And the trade-off between the uniform boosting flatness and quality was tuned to provide the same quality as for the non-flat classifier. In the paper provided at the bottom of the slide, you can find plots for other particle types. we considered how to modify loss function for an adder boost classifier to provide flatness of its signal efficiency on a set of features. Now, let's consider a method which allows to train a neural network with flat signal efficiency without any special modifications of its loss function. This method is called decorrelation using adversarial neural network. The network in this approach consists of two parts. The first one is a classifier that is trained to predict a particle type, for an example. This classifier has its own loss function used for the training. For an example, binary or categorical cross-entropy. So this is just usual neural network without any special modifications. The second part of the network is an adversary network. It takes outputs of the classifier for a particle as inputs and predicts a particle momentum value, for example. The momentum prediction is performed using a multi-classification problem instead of the regression one. For that, all particle momentum values are divided into bins, and each bin represents a separate class. The adversary network predicts a bin for each output of the classifier. The adversary network also uses its own loss function, and in this case it can be a categorical cross-entropy. To provide flat output of the classifier, we should minimize concurrently two loss functions shown on the slide during the neural network training. In case of the particle identification, the first loss function represents quality of a particle momentum reconstruction based on the classifier output for this particle. The second loss function represents quality of the classifier, but also this function penalizes the classifier if it's possible to reconstruct a particle momentum based on its output. The lambda in the loss function is an adjustable parameter which defines a trade-off between the classifier flatness and quality. Consider how this approach works. The figure on the slide is taken from the original paper, and it demonstrates outputs for the decorrelated adversarial network compared to the traditional neural network. Black curve corresponds to the decorrelated network, and the red curve corresponds to the traditional neural network without adversary part. The decorrelated network shows much flatter dependency of its output from the jet invariant mass. These two methods of uniform classifiers were developed for high-energy physics. However, these approaches can be used in other fields where dependency of a classifier output from a set of features is undesirable. That was the last example of flat or uniform classifiers. Let's make summary of this week. So, we considered an example of a particle decay and learned that mass of the mother particle depends on the energies, momenta and masses of the daughter particles. Tracks of the daughter particles are needed to check that the particles originate from the same point and belong to the same decay. Detectors in high-energy physics and their different systems are needed to estimate a particle trajectory, momentum, energy and its type to be able to recognize particle decays and reconstruct parameters of mother particles. We also considered several of the most common detector systems in high-energy physics. The systems are tracking system, ring imaging Cherenkov detector, electromagnetic and hadron colorimeters, and muon system. All these systems recognize particles, measure their energy and momentum, and identify their types. All charged particles have responses in the tracking system that reconstruct their tracks and measures their momentum values. Ring imaging Cherenkov detector identify a particle type based on its track and momentum. Electrons and photons are stopped by the electromagnetic calorimeter, which also measures their energies. Other particles fly further to the hadron calorimeter, and hadron calorimeter stops protons, neutrons, and other particles containing quarks, and estimates their energies. Muons pass all detector systems and are detected in the muon system. Also, we saw different cases in high-energy physics experiments where machine learning can be applied. Machine learning can be used for particle tracks pattern recognition among detector hits and reject ghost tracks, combining tracks into vertices to recognize particle decays and to estimate properties of matter particles. Machine learning can help to increase precision of particle momentum estimation in tracking systems, or to improve ring image recognition in rich subdetectors for better particle type identification. Particle energy estimation and neutral particle identification based on calorimeter responses are also examples of such cases. We detailed discussed how different classifiers can be used for global particle identification based on responses of different systems of the detector and how to train them to provide flatness of signal efficiency on a set of features like particle momentum, transverse momentum, or energy. Finally, if you would like to get more information about machine learning in the high-energy physics, this slide will help you. It provides a list of references to different articles and talks about successful examples. Thank you very much for your attention and see you next week.